All right, welcome back, everyone. Today's explainer is going to serve as our lecture synthesizing the recent and honestly pretty mind-blowing explosion of multi-messenger black hole research. If you've been keeping up with the literature lately, you know we are literally living in a golden age of astrophysics. I mean, we are no longer just theorizing about these extreme objects on whiteboards. We are actively imaging them, we're listening to them, and we're tracking their behavior across the entire span of cosmic history. It's a really exciting time.
So let's quickly hit our syllabus for today. First up, we'll cover imaging the event horizon. Second, we'll dive into extreme accretion and feeding. Third, gravitational waves and expansion. And finally, we'll wrap up with evaporation and cosmic timescales.
All right, starting right off with Section 1, Imaging the Event Horizon.
Now, as you guys already know from your coursework in General Relativity, light simply cannot escape the event horizon. It's the ultimate point of no return. But what we can capture is the telltale shadow that it casts. Because the black hole itself is entirely dark, we have to look closely at the superheated glowing accretion disk surrounding it. The absolutely immense gravity of the black hole actually bends this light, creating this incredibly bright, ring-like structure that perfectly frames the darkness inside. It is direct, undeniable visual evidence of a boundary where the escape velocity equals the speed of light.
You really have to appreciate the sheer scale of the engineering required to actually see that shadow. It is staggering. To resolve an object the size of a donut on the moon, astronomers couldn't just, build a bigger dish. That wouldn't work. Instead, they had to link up these distinct radio observatories all across the planet, literally from Spain down to Antarctica, to synthesize a single Earth-sized virtual telescope. The Event Horizon Telescope, or EHT, collects data for hours, acting a lot like a long exposure on a camera, and then relies on supercomputers to stitch those massive petabytes of data together. And this whole process brilliantly illustrates the scaling of black holes. The EHT managed to give us images of both M87 star and our very own Sagittarius A star. Now, while general relativity governs both of them identically up close, capturing SGR A star was just incredibly difficult. The gas around both of these objects moves at nearly the speed of light. But because SGR A star is about 1,000 times smaller, that gas completes an orbit in mere minutes. That means the brightness is changing rapidly while you're trying to look at it. As one EHT scientist perfectly put it, trying to capture it was like trying to photograph a puppy frantically chasing its tail, especially when you compare it to the sluggish, steady giant that is M87 star.
Moving right along to Section 2, Extreme Accretion and Feeding.
This brings us to a really provocative question, specifically about early universe quasars. We're finding supermassive black holes operating just hundreds of millions of years after the Big Bang. Think about that for a second. This completely challenges our standard models of stellar collapse and gradual mass growth. So how on earth did they get so big, so fast? Do they start out as incredibly heavy seeds right from the get-go, or do they gorge themselves at unprecedented extreme rates? Well, the answer might actually lie in some recent data from the James Webb Space Telescope. Thanks to JWST's integral field spectrograph, we recently discovered LID-568. This is an early universe black hole that is feeding at a staggering 40 times its theoretical Eddington limit. Let that sink in. The Eddington limit is supposed to be the absolute maximum rate a black hole can eat before the outward radiation pressure just pushes all the infalling gas away. Yet here we have an object breaking that limit by a factor of 40. It seems to be utilizing powerful gas outflows as a sort of cosmic release valve to maintain this extreme feasting. So let's contrast this ancient, supercharged growth with what we see in modern observations. Back in the early universe, mass growth likely happened in these massive, single, violent episodes of super Eddington accretion. But in the modern era, things get weird in totally different ways. Take AT2024 TVD, for example. This is a wandering, rogue black hole located far from its galactic center. It completely shredded a passing star in a tidal disruption event, but it generated fast-changing radio signals months after the initial destruction. It's fascinating because it proves that modern black hole feeding can be delayed, highly episodic, and happen completely outside of a traditional galactic core. But if you want to talk about the absolute ceiling of this feeding frenzy, we have to look at the brightest known quasar. Sitting at a mass of roughly 17 billion suns, it requires the consumption of an entire solar mass every single day just to maintain its intense luminosity. 1 sun a day. It is a stunning reminder of the sheer, unimaginable scale of energy conversion happening right now in these accretion disks.
All right, let's switch gears for Section 3, Gravitational Waves and Expansion. Leaving the electromagnetic spectrum entirely, we can look at the newly expanded LIGO-Virgo-KAGRA catalog, which now tracks over 160 collision events, and this data is revealing two very distinct populations of black holes. First, we have a population of smaller, slow-spinning black holes that almost certainly formed from direct stellar collapse. But then we have this distinct population of giants, heavier than 35 solar masses, that spin much, much faster. The crucial takeaway here is that these larger objects are likely second-generation black holes, meaning they were born from the merger of previous black holes. This perfectly proves that there are multiple hierarchical pathways to creating heavier black holes in the cosmos.
And how do we actually measure that? By literally listening to the very specific frequencies of space-time ringing, by analyzing the exact tones, what we call the ring-down frequencies, of these merging events, we can precisely plot the dimensionless spin and mass of the newly formed remnant. It's a lot like how a massive iron bell sounds fundamentally different than a small aluminum one. The exact pitch and decay of the gravitational wave lets us test general relativity in the most extreme dynamical fields possible. It's absolutely brilliant. And what's really exciting is that our precision is rapidly improving. Take the event GW240-615. It was localized to a region of the sky just 6 square degrees across. To put that into perspective, that's an area just 30 times the size of the full moon. By pinpointing a merger with this kind of pinpoint precision, we can actually use gravitational waves as a completely independent standard siren to measure the universe's expansion rate. This is huge because it allows us to cross-check the Hubble constant without having to rely on the traditional cosmic distance ladder.
Finally, let's push into the deep future with Section 4, evaporation and cosmic timescales. To understand Hawking radiation, we have to mash up general relativity with quantum mechanics. You see, space is never truly empty. Virtual particle-antiparticle pairs are constantly, spontaneously popping into existence everywhere. But if this happens right on the razor's edge of an event horizon, the black hole's gravity might pull one particle in while the other manages to escape and become a real particle. Now, the energy required for that escape has to come from somewhere, right? It comes from the black hole itself. So black holes don't just endlessly consume, they actually slowly, constantly leak energy over time.
Let's look at the timeline for this, because it shows an incomprehensibly slow process of total evaporation. For a standard stellar mass black hole, this decay takes far, far longer than the current age of the universe. But as the black hole shrinks, the radiation process accelerates. By the time it arrives at the mass of a large asteroid, it's radiating at about room temperature. When it shrinks further down to the mass of a mountain, it's literally glowing with the heat of our sun. And then, in the very last second of its life, it violently flashes out of existence with the energy of billions of nuclear bombs. Of course, this will happen deep, deep in the future, long after the very last stars in the universe have completely burned out. So as we wrap up today's explainer, I want to leave you with a massive, unresolved paradox to chew on. If a black hole eventually evaporates completely into just random, featureless thermal radiation, what exactly happens to the physical information, the quantum states of every star, every planet, and every single atom it ever consumed? Does that information just vanish from our universe forever, which would totally violate the core tenets of quantum mechanics? Honestly, we still don't know. But the multi-messenger data we are collecting today might just hold the key to finding out tomorrow. Keep studying, keep questioning, and I will see you in the next explainer.